list of symbols used in mechanical translation systems. It's a review process only. So x is the displacement, v is the velocity, a is acceleration, f is force, applied force, fm is f suffix m is opposing force offered by mass, f suffix k opposing force offered by spring or elasticity of the body, f suffix b is opposing force offered by the friction of the body, that is dashpot, capital M is mass, k is stiffness of the spring, b is viscous friction coefficient. These are the terms or symbols used in mechanical translation systems. We are going to use these symbols to model mechanical systems. So I stopped this slide last class. So this is a small introduction to Laplace transform. So hope you are all so familiar with Laplace transform. You might have studied in signals and systems. You might have solved a lot of problems related to Laplace transform. It's a quick review of Laplace transform. So here, first line, this one, Laplace transform of x of t is x of x. At the same time, Laplace transform of dx of t by dt, Laplace transform of dx of t by dt is equal to x into x of s. Important thing related to this particular Laplace transform is, here we have to assume the initial conditions are is equal to 0. That is very, very important, which is related to differentiation and Laplace transform. If you are trying to take Laplace transform of first order differentiation of a system x of t, then which is equal to x into x of x, this is valid when you are assuming the initial conditions are equal to 0. At the same time, if you are trying to take Laplace transform of d square x of t by dt square, then the Laplace transform of this term is equal to x square into x of s. Here also we have to assume that the initial conditions are is equal to 0. So throughout our discussion, we are going to use x of t, Laplace transform of x of t, Laplace transform of dx of d by dt, and this one, Laplace transform of d square x of d by dt square. So whenever you come across these three terms, this is the Laplace transform, and we are going to use these terms throughout our discussion. With this small introduction to Laplace transform, we are going to discuss one problem. First problem. Here I'll just read the problem statement. Write the differential equation of the mechanical system shown in figure and determine the transfer function. So write the differential equation of the mechanical system shown in figure and determine the transfer function. You are seeing a mechanical system. In this mechanical system, you are able to see a mass element 1, mass element 2, spring element 1, spring 2, dashpot, and friction B1 and B2. These are the mechanical elements available in this particular mechanical system. So we are going to write differential equation to this particular system. That is, You know that we are going to find out transfer function. You know that transfer function is nothing but Laplace transform of output to Laplace transform of input. Here input is force. Here input is force and output is x, that is displacement. We are going to find out Laplace transform of force and Laplace transform of displacement, and we are going to find the ratio to determine transfer function of the system. So, if you are if you are correctly listening this particular problem, it is very easy to solve subsequent problems. If you are not listening, then again you will ask a lot of doubts. So, I kindly request you to make a note, and if possible you can write in your notebook. I will give you handouts later, but if you want to practice, please practice. Just see the lecture. Now, here in this particular problem, applied force is f of t, that is the input, and displacement x is the output. So, this one is input and this one is output. We are going to find out the transfer function. Okay, now let me tell you the Laplace transform of input and output. Input is force. So Laplace transform of f of t is f of s. Laplace transform of x, that is output, x is x of s, and Laplace transform of x1 is x1 of s. Then what is this x1 and x? X1 is the output, and that is displacement at the last, and x1 is the displacement happened because of mass element 1. That is, we are going to find out x1 of s. This is, we are going to find out x1 of s and x2 of x of s and f of s to determine transfer function of the mechanical translation system shown in this particular slide. So, our job is to find out x of s divided by f of s. This is the result. We are going to find out x of x by f of s. We have to find this one. That is the result of this particular question. So, in this particular problem, we have been asked to determine the transfer function of the given mechanical system, is shown in the top of this slide. So, in order to solve this particular problem, we need to know how to solve it. Here, the basic constraint is we have two mass elements. We have two mass elements, m1 and m2. So, these are the two mass elements. The differential equations governing the system are given by force balance equations. So, here we are going to find out differential equations related to mass element m1 and m2. We are going to determine these two things. From that, we are going to determine the transfer function. You can even ask me, why should we consider mass element? Mass is the reference. Okay, mass is the reference for mechanical systems, and it is not possible to use the spring and the dashboard for reference, because that is the nature of the system is entirely different. Mass is the ideal one, so we are considering mass element to model or finding the differential equation of the given mechanical translation systems. So, first we are going to consider first mass element, and then we are going to consider second mass element to determine the transfer function. First we are going to find out differential equations related to this mass element and then this mass element. So, first mass element. Now, we should know how many forces are acting on this mass element 1. So, in order to find out how many forces are acting in this mass element, first we have to find out how many links are there, how many links are touching in this particular mass element. As far as this particular problem concerned, mass element 1 is connected with a spring, that is K1, then dashpot, then another spring K2, then a friction B1, and again the mass. So these are the how many? 1, 2, 3, 4, 5. 5 different things are connected in this particular mass element 1. We applied force on mass element 2. You can find f of t only on M2. Is it correct? At only one mass we have applied force on M2, and we have not applied force on any other elements. You must be very hence no force is applied on M1, and you know that Newton's second law, if you are applying force, there will be equal opposite force will be there is exist. Is it correct? So sum of the applied force and the opposing force are equal to 0. Here regarding mass element 1, we have no applied force, we have one, it has only opposing force. That opposing force are due to the mass itself, mass M1, the spring K1, dashpot B, and spring K2, and the friction B1. So we have 5 different opposing force. One is F suffix M1, second one is F suffix B1, third one is F suffix B, fourth one is F suffix K1, and the fifth one is F suffix K. 1, 2, 3, 4, 5. All these forces are opposing force, and we have the mass element M1, there is no force is applied, so all are opposing force. Hence we are going to write using Newton's second law, the last one, Newton's second law, the sum of force acting on this mass element is equal to 0. Sum of force acting on this mass element is equal to 0. So these are the forces, that is Fm1, Fb1, Fb, Fk1, F suffix k. When you are adding all these forces, then the sum is equal to 0, that is Fm1 plus Fb1 plus Fb2, Fb plus Fk1 plus Fk is equal to 0. This is using Newton's second law. Applied force is equal to opposing force, or we can even say that sum of applied and opposing force are equal to 0. Now we are going to write differential equations related to all these forces. First we are going to discuss the differential equation of mass element Fm1. So here Fm suffix 1 is equal to m1 into d square x1 by dt square. Before writing this particular equations, we need to consider the displacement. The displacement related to the first mass element is x1. Displacement related to first mass element is x1. You can see in the top of this particular figure, your circle potter, just have a look. So displacement related to the mass element is x1. Okay, so the displacement related to this particular mass element is x1. Hence f suffix f m suffix 1 is equal to m1 d square x1 by dt square. So x1 is related to displacement because displacement happened because of mass element 1 applied force. Next one is FB1. FB1. FB1, B is nothing but the friction. So B is equal to FB1 is equal to B into dx1 by dt. So these equations we have already discussed. I am just giving the result. Now third one is Fk1. K1 is nothing but spring. K1 is nothing but related to spring. So Fk1 is equal to K1 into x1. Fk is equal to K into x1 minus x. Here you have to be very careful. You have to be very careful in writing this equation. Now, you take the spring K. Spring K is connected in between mass element M1 and M2. All of you kindly listen. This spring and dashpot B both are common to mass element M1 and M2. If it is common to these two things, then you have to consider the displacement x1 and x2. So rightly pointing out, you have to go back to a list of simples that I have told you that a spring or dashpot not connected to any reference. So we have discussed 5 different occasions. One is ideal mass element, ideal spring connected with reference, ideal spring connected with no reference, that is connected with two other things, ideal dashpot connected with reference, ideal dashpot not connected with reference. This we have discussed in our last lecture. So according to this problem, we have two elements. One is dashpot B and spring K. These two elements are not connected with any reference, and these two are connected with mass element 1 and mass element 2. Because of this, it will exhibit displacement in x1 and x1 and x, two different displacement. Because of that, with reference to mass element m1, the displacement we are going to consider x1 minus x. Because of this, the displacement mass element 1, the displacement related to the spring is Fk is equal to K into x1 minus x2. At the same time, if you are considering with respect to m2, we have to write like K into x minus x1. Similarly, we are going to discuss about dashpot B. FB is equal to B into d by dt of x1 minus x, because this dashpot B and the spring are common to the mass element m1 and m2. Now, before going to next slide, I want you people to ask whether you have you people to tell me whether you have understood this concept or if you have any doubts, because this is the important slide. Without understanding this slide, I don't want to move to some next slide. Please, I welcome questions. Please, one by one ask. You have to ask me, otherwise I'll wait for 1 minute and I will go to next slide. So because it's very vital one. So I have introduced mass element 1 and I told you that all are opposing force, and we have written the differential equation to each and every elements, and I told you that this is very important. F suffix k and F suffix b and these two are very, very important to understand this concept. Any question? Using Newton's second law, I told you that sum of all forces up on mass element 1 is equal to 0. So I told you that there is no applied force on this particular mass element. Hence, we are going to sum all the opposing force on this mass element. So when we are adding all these forces, the sum will become 0. Now we are going to substitute the value of all these force equations, and we can find, when you are substituting value of f suffix m1, you will get m1 into d square x1 by dt square plus b1 dx1 by dt plus b dx1 minus x divided by dt plus k1x plus k into x1 minus x is equal to 0. So I simply substituted the value of all these forces acting on the mass element m1. You will get this equation. These equations are available here, the top of the slide. Now we are going to take Laplace transform of this particular equation. So these Laplace transform also we have already given. The first slide itself I have given the Laplace transform. Now Laplace transform of m1 into d square x1 by dt square is equal to m1 s square x1 of s. Okay, this is the Laplace transform of the term m1 d square x1 by dt square. Similarly, you are going to substitute Laplace transform of other terms. So Laplace transform of the second one is b1 s x1 of x. Laplace transform of the third term is b s x1 of s minus x of s. Similarly, k1 into x1, the Laplace transform is k1 into x1 of s, and finally k into x1 of x, the Laplace transform is k into x1 of s minus x of s, which is equal to 0. So I have not done anything. We have written the Newton's second law equation and substituted the value of each and every components or differential equations already listed in this slide, and we have taken Laplace transform of individual terms. That is, there is no wonder here. Substitute and take Laplace transform. That's it. And this is the Laplace transform. Now we are going to rearrange this equation. Here we have two terms. One is x1 of s and x2 of s. We are going to separate x1 of s and x2 of s. Okay, simply you have multiplied. For example, you can take this. You take this term bs b into s x1 of s into x1 of x minus x of s. You can multiply this bs inside, you will get bs x1 of s and b1 when you are this is bs into x of s, so you have to multiply bs inside and rearrange this equation in terms of x1 of s and x2 of s. I simply done, we multiply inside and rearranged. There is no, both equations are same. I have rearranged the equations. That is, when we are doing it, we will get m1 s square x1 of s plus b1 s x1 of s plus bs x1 of s plus k1 x1 x of s plus k into x1 of s minus bs x of s minus k into x of s is equal to 0. There is no change. Both the equations are same, but I have rearranged by multiplying, after multiplying bs and k inside the bracket. That's it. Taken x of 1 outside and x of s outside, and again I have rearranged. So from this equation I have taken x1 of s outside and x2 of s outside, and I have written the equation. So x1 of s, when I am taking x1 of s outside, I will get m1 s square plus b1 b1 plus b s plus k1 plus k minus, when I am taking x of s outside, I will get bs plus k, which is equal to 0. Now I can write this equation like, because it's 0 here, I am going to equate this equation. So I am going to change the place of this particular x of s right hand side. So x1 of s and m1 s square plus b1 plus bs plus k1 plus k is equal to x of s into bs plus k. Here, which one is here? This x of s is the output displacement. X of s is the output, and this is again output of the mass element m1. Now I am going to find out, now I am going to write x1 of s in terms of x of s. It's simple multiplications only. So I have interchanged the terms, coefficients, and I have written, I can write like x1 of s is equal to x of s, the last equation, x of s into bs plus k divided by m1 s square plus b1 plus bs plus k1 plus k, and we are going to consider this as equation 1. So we are going to consider this as equation 1. Next one is, we are going to move to mass element 2. Free body diagram of mass element 2. So we are going to consider, we have completed mass element 1, and we are going to consider the force acting on mass element 1. What are the force acting on mass element 1? So this we have discussed about mass element m1. Now we are going to discuss about force or free body diagram of mass element m2. I told you that at one place we have applied force f of t. That force is applied on mass element m2. This is the applied force, and we don't find any applied force on mass element m1, and the only one place the force is applied is mass element m2. Because of this applied force, there will be opposing force due to connected elements. First opposing force is from the mass element m2, that is Fm2. Then the opposing force is related to friction P2. Okay, that is the friction between mass element m2 and the reference, because mass is lying on a ground, something like that you can think. Now the opposing force related to dashpot, that is connected in between mass element m1 and m2, and finally the spring that is connected in between m2 and m1, the spring constant is k. So F suffix k. So these are the force acting on mass element m2. Now we need to know the differential equations on this opposing force. For example, Fm2, and here I want to tell you that displacement is x1, displacement is x, and when we are considering fb and fk. Here we have to find the displacement with respect to x1 and x. Okay, now so force balance equation, that is m2 fm2 is equal to m2 into d square x by dt square, and fb2 is equal to b2 into dx by dt, the second equation. The third equation, f suffix b. So this particular dashpot is in between mass element m2 and m1, hence the differential equation is equal, f suffix b is equal to b into d by dt of x minus x1. So I told you that with respect to m1 you have to write displacement like x1 minus x. Now we are going to write equation with respect to mass element m2, hence we have to write the displacement like x minus x1. Similarly, the force acting because of a spring f suffix k is equal to spring constant k into x minus x1. These are the differential equations of different force acting on mass element m2. We know that Newton's second law says applied force is equal to opposing force. Here applied force is F of t. Opposing force, we have four different opposing force. When you are adding all these force, the sum is equal to 0. This is the Newton's second law. Now by Newton's second law, the applied force F of t is equal to, the applied force F of t is equal to the opposing force due to mass element m2, the opposing force related to the friction b2, opposing force related to dashpot which is common to m1 and m2 fb, and the opposing force related to spring f suffix k which is contained in between m1 and m2. This is the force balance equation, and which is related to free body diagram of mass element 2, that is force, applied force is equal to opposing force. Okay, f of t is equal to this one. Now we are going to write the corresponding differential equations of all these terms. So f of t, this is the applied force, which is equal to differential equation related to f suffix m2, then differential equation related to f suffix b2, f suffix b, then f suffix k. I simply substituted the value of different terms, and we have written this equation. Now we are going to take Laplace transform of this equation. So Laplace transform of f of t is f of s. Laplace transform of f of t is f of s. Laplace transform of m2 d square x by dt square is this one, and second term this one, third term is this one, and fourth term is this one. So this is simply, I have written Laplace transform of differential equations. There is nothing new one here. We have already discussed in the previous slide. So Laplace transform of m2 d square x by dt square is equal to m2 s square x of s. Then next one is b2 s into x of s. Then plus b into s x1 of x of s minus x1 of s, because here we have d by dt of x minus x1. So x of s minus x1 of s, then plus k into x of s minus x1 of s. Now we are going to rearrange this equation in terms of x of s and x1 of s. So we have here two different terms, x of s and x1 of s. I am going to rearrange this equation. When I am rearranging, separating x of s and x1 of s, I will get f of s is equal to f of x is equal to x of s into m2 s square plus b2 plus b into s plus k. So this is these are the terms related to x of s, and we have another term x1 of s into bs plus k. You have to consider this is equation 1. We have obtained two equations which is corresponding to mass element 1 and mass element 2. These are the two equations. So first one is equation 1 and the second one is equation 2. This we have obtained by considering mass element 1, and this one we have obtained obtained this equation by considering mass element m2. Now we are going to substitute the value of x1 of x in this particular equation. Okay. So we are going to substitute the value of x1 of s in the final equation f of x. Substituting x1 of s in the above equation. Okay. When you are substituting the above equation, so you will get, so we are going to substitute this equation in this particular place. You will get x of s into m2 s square plus b2 plus bs plus k minus, here we are going to replace this x1 of s with this equation, hence you are going to substitute this one. So x of s into, so this one you are simply replacing it. So x of s into bs plus k the whole square divided by m1 s square plus b1 plus bs plus k1 plus k, which is equal to f of s. I simply substitute, simple mathematical substitution. Now we have to rearrange or cross multiplication, whatever you want. Why we need to find out transfer function. Transfer function is x of x by f of x. So we have this equation, it consists of x of s as well as f of s. We have to rearrange these equations by multiplying, cross multiplication, or etc. to determine the transfer function. Here the common terms are x of x. So you can take this x of s outside. When you are taking this x of s outside and cross multiplying these two terms, you will get x of s into this term, okay, this term, and into this term, second term, minus bs plus k the whole square divided by this term. So we have to simply rearrange this equation to obtain x of s and f of s. By doing this, you will get x of s by f of s is equal to m1 s square plus b1 plus bs plus k1 plus k divided by m2 s square plus b2 plus bs plus k into m1 s square plus b1 plus bs plus k1 plus k minus bs plus k the whole square. This is the transfer function of this particular given problem. That is, this is the mechanical this problem, this particular mechanical device. This is the transfer function. Once we obtain the transfer function, we can easily find the response of the transfer function, response of the system, using by giving step signal or impulse signal, something like that. So whatever may be the situation, whatever may be the problem given to you, you have to find out the transfer function. So final result, this is the final this one, the last equation, x of x and divided by f of s, the final equation. So you may be asked to determine transfer function of the given mechanical translation system. Here the given mechanical translation system is displayed on top of the slide here, and we have determined the transfer function by considering these two mass elements, and we obtained the transfer function of the given mechanical translation system. This is the answer.